Okay, so graphing functions is a strategy that's often used to get a visual picture of what a function looks like that you can't just get from the formula. It's also often used to analyze functions or compare them because you can look at multiple functions at one time. So you've probably seen a graph of something before, but I'm going to go over what a basic graph is so we're all on the same page. A basic graph consists of these two perpendicular lines called axes. The horizontal one is the x-axis and the vertical one is called the y-axis. And then you have these little tick marks to indicate the scale. So sometimes you want each tick mark to be 1 unit or 5 units or 25 units depending on what sort of function you're looking at. If they're unmarked, it usually means that there's just 1 unit between them. And so then on the graph you can plot points like this, which are in the form x comma y. So your first number is going to be your horizontal component, and the second number is the vertical component. So to plot the point 1 comma 3, that's going to be horizontal 1 from the origin and then up 3. And by the way, up on the y-axis is positive numbers and down is negative numbers. To the right on the x-axis is positive numbers and to the left is negative numbers. But here we have the point 1 comma 3. So now let's do the point 2 comma negative 1 just as another example. We move over 2 horizontally and down 1 vertically to get the point 2 comma negative 1. So that's basic plotting of points on coordinate plane. This is called a coordinate plane or a graph. When someone says graph, they're really talking about the graph of a function. And so let's do an example of that. Here's y equals x plus 1. The idea of graphing a function is to pair your basic input with the output. So the input is the horizontal component and the output is the vertical component. In this case, x comma x plus 1. So we're going to plot all of these points for all x in our plane, or for all x that we want to plot it for. So let's to figure out what that's going to look like, we're going to plot points that we can calculate and then connect those together to get an idea of what the entire function looks like. So with x equals 0, then y is going to be 0 plus 1. So we're going to plot 0 with 1. 1 is going to go with 1 plus 1, that's 2. And 2 is going to go with 2 plus 1 is 3. So here's 3 points. Now we can plot these on our axes. I'll draw some quick tick marks. These are actually called grid lines, not tick marks. But okay, 0 comma 1, so that's 0 in the horizontal direction, but 1 up in the vertical direction. 1 over and 2 up is 1 comma 2, and then 2 over and 3 up. Honestly, these tick marks ought to be equally spaced, but you know, for the purposes of a sketch, it's not that important. So after you've plotted some points, you can connect the dots, and this is basically what your function is going to look like. In this case, it ought to look like a perfectly straight line. And so you actually only need to plot 2 points to know what that's going to look like, as long as you know it's going to be a straight line. We're going to do another example where we plot a lot more points than that, but if you're familiar with the function, then like you might recognize that this is a linear function, and you see line right there in linear, and so you know that that's only going to need 2 points to get an idea of what it looks like. This is linear, by the way, because it doesn't have an x squared or anything like that. It's just x maybe multiplied by a constant and added with a constant. So that makes a linear function. But now let's look at a more complicated one that's not just a straight line. So graph f of x equals x squared. I'm going to set y equal to x squared and now plot these points. Negative 3 is going to go with negative 3 squared, which is 9. Negative 2 goes with 4. Negative 1 goes with 1, etc. So you need to plot more points the less familiar you are with the function. And if you want these pictures to be perfect, then you can get software to do it, but sketching is usually good for just basic purposes. So I'm going to label this graph negative 1, negative 2, negative 3, 1, 2, 3, and then I'm going to make the vertical axis be 2 per tick mark. So it's negative 2, negative 6, negative 10. Okay, and same for the vertical one. 2, 6, 10. You don't have to label each tick mark as long as you establish the scale. So negative 3 goes with 9, that's between 8 and 10. Negative 2 goes with 4, that's right there. Negative 1 goes with 1, 0. Then we have 1 again, 2 goes with that one, 3 goes with that one. So we get this kind of cup shape when you connect these dots. And this is known as a parabola. And that's the shape that you get when you graph quadratic equations. So you get a parabola, and that's what a parabola looks like. So that's another example of graphing a function. Now that you have a pretty firm idea of what a graph of a function is, I want to talk about transformations. And this lets you infer what a graph of a complicated function is going to look like by knowing what the graph that's based on looks like. The graph of the function that it's based on, that is. So for example, I know with the graph of y equals f of x, looks like. But now I want to know what y equals f of x all plus 1 looks like. So this is true generally for any function, but I'm going to demonstrate it with this simple example. F of x equals x gives you this straight line. So y equals f of x plus 1, what's that going to look like? Well, when you think about it, this is just take every y coordinate and add 1 to it. So what used to be here, I'm going to add 1 to that y coordinate. So this just moves everything up by 1 unit. Yeah, I didn't draw that perfectly, but ought to be the exact same line, just moved up 1 unit, and that's called a vertical translation. Now, if you had a -1 here or a -10, that would be moving it down. So it's pretty simple to see. You're just changing the y coordinate there. Y equals 2 times f of x. Well, this is also pretty simple. You're just gonna double each y coordinate. So the ones that are pretty small is not going to make quite as much of a difference. The one that have big y coordinates is going to make a big difference. So you end up with what's called a stretch. This is called a vertical stretch by 2, and that's what multiplying f of x by 2 makes. Now, if you divide f of x by 3 or multiply it by 1/3, that's going to give you what's called a compression by the same logic. So yeah, I'm really not drawing these very well. This ought to all be straight lines. So that's a vertical compression by 3 by the same logic. Y equals negative f of x, that's going to take every y coordinate and then map it to the corresponding one downstairs, or the negative one, so that gives you a reflection across the x-axis. So that's basic vertical transformations. It's not a bad idea to just sort of memorize all of these, and then you know, if you need to, you can work it out to prove it to yourself, but it's probably better to just memorize them so you can recognize them really quick. Now let's talk about horizontal transformations. These are a little bit trickier. They don't do what you expect. So y equals f of x, I'm going to use x again, the basic function. Y equals f of x plus 2, you might think this is going to be a horizontal shift to the right because you got a positive number in here, so you're moving more towards the positive side, but it's actually going to be a shift to the left, and I want to give you some reasoning for that. So if we have just an arbitrary a here, where x equals a, that goes with f of a, let's look at, I'm going to call this g of x. Let's look at what g looks like with regards to a and f of a. So what's g of a? Well, g of a is f of a plus 2, right? That comes straight from this definition. So what the y coordinate that we used to hit, that f hits at a plus 2, that's about here, g is actually going to hit at a. So it hits it earlier. And another way is g of what is f of a? When do we hit that original y coordinate? Well, that's going to be at a minus 2, right? Because you add 2 to a minus 2 and you get a. So we're hitting everything a little bit earlier than we used to. So a minus 2 is maybe here. We're hitting that f of a there. So we're hitting everything earlier. So this is actually a shift to the left when you add 2 inside the parentheses. And if you subtract 2 inside the parentheses, you get a shift to the right. So it's the opposite of what you might expect. And again, you ought to just memorize that, but this is how you can reason it out. And horizontal translations and other transformations often do the opposite of what you expect. So here's another example. Y equals f of 2x. You might think this is going to be a stretch, but it's actually going to be a compression. And that's because if I call this h of x, what's h of a? H of a is going to be f of 2a. So that y coordinate that we used to not hit until 2 times a, we're now going to hit way early. We're going to hit at a. So this gives you a horizontal compression, which in this case looks like a vertical stretch, but it won't always be that way. You get a horizontal compression, like I'm pushing in on both sides because we're hitting everything earlier. And same with you get a horizontal stretch if you're dividing by a number, like multiplying by 1/3. Then you get a horizontal stretch instead of a compression by the same logic. Y equals f of negative x is going to be it's going to be a reflection across the y-axis instead of the x-axis. So you're going to get this, and that's because if we call this, I don't know, d of x, d of a is going to be what used to be f of negative a. So what we're going to hit at a for this function is what we used to hit at negative a. So you're looking at the blue line, negative a is maybe here. We used to hit that at negative a, but for this transformed function, we hit that at a. So you reflect it across the y-axis. That's what f of negative x does. So again, you ought to just memorize those, but that's how you can reason them out. And it's really important to know transformations, because if you look at a function like this, you have no idea what that graph is going to look like, but you know what y equals x squared looks like. So if you recognize that we're just replacing the x with an x minus 1, so that's a horizontal shift, and then multiplying that by 3, that's a vertical stretch, and then adding 4 to that, that's a vertical translation, you can get a very good picture of what this graph looks like in no time at all by just knowing your transformations and knowing the graphs of simple functions. And kind of as an aside, this is why it's important to know how to complete the square, because these functions are actually the same. These are the same function. But if you can complete the square on this bottom one, then you get this much more informative function that has the same graph. So that's basic graphing of functions and transformations. I hope I didn't go through that too quickly. We'll do some examples in the next video. But in the meantime, thanks for watching, and I'll see you next time.